Thank you. Thank you for organizers. And well, definitely there is an English mistake. I hope you can find another mistake. So. Okay, well, let me tell you the outline of the talk. So first, well, I'm going to introduce what's going on in such geometric questions or how to approach the eigenvalue problems through the parabolic method. And then I will give you some introductions, and then I will introduce the one of the important idea of the clever, and I will discuss what's the problem and what is the advantage of this method and the downside of the method. And then I will introduce the parabolic method, and then I will apply the method to the nonlinear eigenvalue problems, and that is the joint work with the Vasquez. And then if you want to read it, then you can find the paper. And also I will discuss the Galfand problem, which looks like eigenvalue problem, but you have an exponential nonlinearity at the right hand side. And also I will talk a little bit about the nonlinear eigenvalue problems for the fully nonlinear equation. And this is a joint work with Sujan Kim, who's there. Okay. And okay, let me talk about our observation. So let's say you have a heat equation. Then one of the simple solution is a fundamental solution. And then it is like a bell type solution. It has a normal distribution. And if you take a log of it, then you have a minus x squared, which is concave. So it is very natural to ask a log concavity of the solution of the heat equation, because the fundamental solution itself has a log concavity. And the question could be what about the general solutions? And let me give a simple computation and then see what is the problem in the computation. So let's say you have nonlinear eigenvalue problems with u to the p, and if p is 1, then definitely you have a constant in front of it. And if p is different from 1, you can scale it and then you can make it 1. And then let's say I try to show the solution is log concave. And then you take a log of u, and that is a v, and drive the equation for v. And then what I want to show is I take a second differential of v and take a maximum of it in every point and in every direction. I want to show there is a, I want to show this is non-positive. So in other words, if it is positive, then you have a contradiction. Okay. So then, well, that point could be a boundary point or interior point. And boundary point is relatively easy. So if you take a second differential, then you can write down in this form in terms of u. And let's say your gradient of u is not 0 and boundary is strictly convex. Then you can show this value is actually negative. Okay, so there are two possible choices. Alpha could be tangential direction or normal direction. And if alpha is a normal direction, and let's say your second differential of this u is uniformly bounded, that is a very tricky part too. But at least in the Laplace case, it is okay. And if that one is bounded, and let's say u goes to 0, then this one goes to 0, but this one goes to negative value. So all of things goes to negative value. So now, let's say your direction is tangential direction. Then tangential first differential will be 0. And what about the second differential? And the second differential, this is u, and second differential of u is like a first differential of u times curvature of the boundary. And the first differential normal direction of u is negative because you have a positive value and you are approaching to the 0 value. So it's a negative. So all of these values is 0. So in the other words, if you are able to show gradient is non-zero, then your second differential of v is negative if your boundary is strictly convex. So it's nothing to do with about the second differential of u, but it's really about the first differential of u. So that is one observation. And what about if your point is interior point? You simply take a second differential of it, and the maximum was achieved at some point, and then that is the maximum value of the pure second differentials. So in other words, that is Eigen direction. And if you look at the mixed differential, then that will be 0. Because alpha is really maximum of all of pure second differentials. Okay, so it will be Eigen direction. So mixed direction will be 0. And the second differential has a sign, and first differential will be 0. So then you have lots of information in this equation. First of all, this one is negative, and this one is 0. This is positive. That is a bad term. And if this is, well, if you are able to show all of these things is positive, and this one is negative, and let's say you don't have this term, then you have a contradiction. Okay. So first observation is you have a trouble term here. And now, this is also problem term. Because we are talking about the maximum of second differentials. So we have information about the second differentials, but we don't have any information about the first derivative. So we want to eliminate this term. So that's why we select P is 1. So local concavity works for the linear case because of this term. And what about this part? We want to make this is positive. In the other words, this one is negative. So let's say, well, if you just think about the difficulty here, then P should be less than or equal to 1 to make it positive. So somehow you have a little bit cool direction if P is less than 1. So you have lots of things going on, and one problem is this one, and you have 3 parts. Okay? So, well, we selected 1 to remove this term, so that's why we have local concavity for the linear case. And also we have a little bit good terms if P is less than 1. And, but we don't know how to handle these terms.
Yeah. Where are you headed? This existence of the Eigen? Are you headed to the existence, or?
Well, I want to show the local concavity
of the Eigen
first eigenfunction.
Okay.
Yeah. Then I try to show my first eigenfunction is local concave. Then I realize that P should be 1. Otherwise, the method doesn't work. Okay. So now let me introduce the idea of forever. And then, well, we end up with the same problem. So now V is a local view as we did, and then we have this equation, okay, for general P. And then forever consider the very general equation in this form. And then, but the important thing is this Aij doesn't depend on the V. It just depends on the gradient of V. That is very, very important. Otherwise, the method doesn't work. Okay. So his idea is he looks at the second difference quotient somehow, and then he want to show this is non-positive. That means it will be concave. So let's say it is a positive, the maximum is positive, then he drives the contradiction. And then what is the great thing of this method? So let's say you have a maximum of this value at some point, then the gradient will be 0. So let's say you take a differential in x direction, then at this point it will be 0. So you have this equality. And if you take a differential in y, then you don't have this term, so you have a differential of this one, and then you have this one. So what does it mean? So you have x naught, y naught, and the middle point, x naught plus y naught over 2. And if this second differential quotient has a maximum, then the gradient at these 3 points are equal to each other. So in the other words, the diffusion coefficient will be equal to each other. So you can add them and subtract them freely. Okay. So then, well, let's say this the same gradient is large U, and then you write down the equation. Then you can write down the equation for your Mij. Mij is the second differential of this quantity. Then you have, if you put some condition on the B, then you have some kind of contradictions. Okay. So the main idea, so the condition on the B is you have some condition basically, right? And that one is exactly equivalent to the condition for P. Okay. If P is a sublinear, then Kramer's idea works. Okay. So, well, if you follow carefully, then you can see that, but let me skip. So, it is successful for the nonlinear eigenvalue problems if P is less than 1. Okay? And then, but it doesn't successful at all if P is greater than 1. And also, this is a method for the elliptic problem. So, it doesn't work for the parabolic. But if you use T as a certain sign, right sign, so then, for example, if you look at Laplace of U and use of T is like 0, and let's say this is has a certain sign, right? Then let's say it looks like this. Then let's say this one is like a positive operator. Then you can think like an elliptic operator. Then you can apply his method. But if you use the sign of use of T is changing, then the method doesn't work. So our problem is, well, what if P is greater than 1? And what about the parabolic flush? That was the main question here. And then the parabolic method is pretty simple. So you look at the parabolic equation, and then you look at the equation for the V, which is log of U, then you end up with this one. And then the difference between the elliptic equation and parabolic equation is the following. So in the elliptic equation, you get a solution, but you don't have anything in your hand at the beginning. You certainly get the solution through your method. But in the parabolic equation, you start with your initial data, which you can choose whatever you want. And then you can follow the force. So that is a good advantage in the parabolic equation. So let's say you expect a certain behavior at the limit, then you can start with a very nice data which has such a property. That's what I want to do here. So, well, let's say my initial V is concave. In the other words, U is log concave. And let's say it is a strictly concave, then the supremum of second differential will be initially negative, and let's say it is 0 at a certain time. Okay, then I want to create some contradiction there. So in the other words, this value will be negative all the time. It means V is concave and U is log concave. Okay. So the boundary point is not a problem as long as the gradient of U is not 0. So you have a Hopper principle, so you have no problem. And let's say x sub naught is the interior point. And then we look at the evolution of the second differentials. Then it's simple. You just take a second differential and then you get this equation. And then now I want to create a contradiction if this the maximum is achieved at a certain time, and let's say the maximum value is 0. Then at the maximum, the time differential is positive. So you can see this is positive. At the maximum point, the second differential is negative, and the first differential is 0. This is 0. This is negative. This is positive, and this is a trouble term because it's a positive term. So let's analyze this one. So at the maximum point and maximum direction, so V sub alpha is the maximum of pure second differentials, so it is eigenvalue, so mixed differential will be 0. So this part will be simply V sub alpha squared. Okay? So this one is 0, and this is negative, and this is time differentials. So somehow at the maximum point, roughly saying, the maximum, let's say it's the max of v sub alpha alpha, and then it depends on the t. And time differential looks like this one. So, and we started with a negative value, and it's increasing, but as g goes to 0, then this value is getting smaller and smaller. Somehow, it never crosses 0 value. So it will stay negative for all time. So that's the advantage of this method. So this term is not a problem anymore through this method. Okay, so then let me give you the computation in the pulse medium equation. It's more complicated, but it has a similar part, but it has a difficulties. So, and in the pulse medium equation, it has this form, and then your function is u to the m, and it is a degenerated equation because Laplace of u will be m gradient u to the m minus 1 and gradient of u. Your diffusion coefficient will be 0 if u is 0. So it's nonlinear. And well, u to the m minus 1 is the pressure, and if you write down the equation in terms of the pressure, you end up with this one. And your v, the diffusion coefficient, depends on the v. And then this is difficult part. So in the Krebs method, this part was depends on the gradient of u. So that's why his method works, because the gradient is equal to each other at different 3 points, but the v will be maybe different. So you have a different equation. So now let's try to apply our parabolic method in this problem, see what happens. And then the conclusion is, if initial pressure is scaled to concave, then it will stay scaled to concave forever. And then computation is pretty important. We're going to use it later. So let me introduce how it works. So I want to show square root of v is concave. So v is w square. And I want to show the concavity of w. And then you can take a one differential and second differential and plug in there. And then, well, then you're going to have difficult terms. So if you take a second differential, then you throw the one differential here and the other differential here. Then you have this term, and that is a trouble term. Why is that? Because we are looking at the maximum of the second differentials. But here, the differential is distributed in the other two terms, so you don't know how to control it. And what about the other terms? Here, you have Laplace of w. Let's think alpha is equal to beta. Then this is w sub alpha squared, which is positive. And what about the Laplace of w? And it was concave up to that time. So this one has a sign which is negative. So it's great. And here you have w sub alpha alpha, but you are looking at the maximum point where your maximum value is 0. So this term goes away. Okay. And what about this term? You have w sub alpha and the other one, the mixed one is 0, and also w sub alpha alpha is 0. So this one goes away. Similarly, this term goes away. So only problem comes right here. So how can you handle this term? And the idea is changing the directions. So instead of looking at the w sub alpha alpha, we look at the w sub alpha beta and eta alpha eta beta. But eta alpha and eta beta will be exactly I wrote down here. So this at the origin, it is exactly like the direction where the maximum was achieved. And then if x is away from that point, then we teeter around it. And it's like a quadratic perturbation away from that direction. And then we want to create extra terms to kill that bad term. And that's the main idea. and then the computation basically works. So you need to match these things very carefully to create extra terms, which is this one. So this is the term which has original equation, and this is the term that we created by changing the direction. And if C alpha is satisfied this equation, then we don't have this term, and the other term is good, so method works. That's a simple computation. And that's the way to prove a square root concavity. Well, it has a lot of details, but I just gave you the key part. So now let's go back to the nonlinear eigenvalue problems. And this is our problem, and this problem was started by Bresk and Lee at 76, and they showed log of first eigenfunction is concave. And basically they use the probability method, and then and there you have a fundamental solution which is log concave, and you have integral things, and the integral basically preserve log concavity and so on, and those are the stories. And that one only works when P is 1, and Kreva introduced the new proof at 83, and he proved the log concavity when P is 1, and Cavo extended the Kreva's idea for the sublinear case. And then Professor Changshu Lin made a very wonderful result, and he showed, this one includes even the superlinear case. And he showed the uniqueness of energy minimizer and the convexity of the level set of this energy minimizer. And that is actually, this uniqueness is a very important open problems. So that is the uniqueness of the ground state for the nonlinear problem. And I hope my geometric solution will give you some insight or barriers for such problems. Okay, and then there is another result for Gladys and Grossi, and he looked at the corresponding energy, and let's say that energy is converging to Sobolev constant, and this exponent is converging to the critical point. Then if this point value is pretty close there, then level set is convex. And then we studied the Parabolic Method for a long time, and it started with the Todi-Daskalopoulos and Hamilton, and we showed the square root concavity in the Porous medium equation. And also, Todi and I showed log concavity in the flame propagation. Here, at the interior, you have a heat equation, which is pretty simple, but the boundary is a free boundary, so your boundary is moving. So computation is pretty tough there. And also we showed the similar result for the Stefan problem, Hill-Shell problem. And in the porous medium problem, the computation is quite lousy. And then I simplified, and then I showed the power concavity in the P-Laplace case. And this exponent is really related with the homogeneity of the operator. And then this is like a conservation of geometry structure. Initially, let's say you have a log concavity or square root concavity, and then it will stay for all time. And the next story is eventual concavity. Like let's say you have any initial data whose L1 norm is bounded and let it go, then you will converge it to the self-similar solution. And then self-similar solution is a very special geometry structure. And the question is whether my general solution has a geometry, such a geometry structure in finite time. And that is an eventual concavity. And this one is really related with regularity, basically. Because the control of the second differential tells you the geometry structure. So we basically showed CK convergence of the general solution to the my self-similar solution. Let's say you have a C2 convergence, and let's say your limit is concave. Then, well, your second differential will be negative infinite time because of the C2 convergence. So that's why you have geometry structure in finite time, and also we showed for the P-Laplace case. Okay, so now let's go over the linear eigenvalue problems. It will tell us all of the steps, and then I will mention a little bit about the nonlinear case. And well, as we did, well, we take a log of u and look at the evolution, and then we know how to show if the solution will be log concave if initial data is log concave, and that part is done. Okay, and I'm going to tell you the other part. So let's say you have initial data, and then you can make as a linear sum of the eigen functions. Then your solution will have this form. And then all of lambda I is eigenvalues and the pi sub n is eigenfunctions. Then your solution is this form. And then the smallest eigenvalue will be leading order term when t goes to 0. So this is the leading part, and you have the other part. Okay? And this function will be the first eigenfunction. Somehow, if you follow up your parabolic flow, then, well, let's say your initial data has a very arbitrary shape, and let it go. But as time goes, your solution forget your initial data because already a long time passed. So it smooths out, and it's getting closer and closer to your first eigenfunction. So that's the very important approximation. So here is the approximation landmark. So since your solution goes to 0, so I will multiply this exponential function so that your u function has order 1 size, and let it go, then it will converge to first eigenfunction with this rate. And we showed actually the convergence is C-infinite convergence. And then that can be done simply by taking the difference of this part and write down equation, and eta is basically this difference, and get the estimate. Then that's it. It's a very simple argument. And then we already showed the preservation of the log concavity. Let's say your initial data is log concave, and it will be log concave forever. So then what happens? So let's say I choose a log concave initial data, then it will be log concave forever. And this one is log concave. And the second differential is converging to here. So this one will be log concave, basically. And that's it. It's a very easy proof. And then also we can show strict log concavity. And that is a different story. So we already know our eigenfunction, the second differential of our eigenfunction has a non-positive value. And we want to show actually is negative. So in the other words, let's say you have zero maximum at the interior, then we want to create a contradiction. And that is like a strong maximum principle. Okay? And then, but in the strong maximum principle, basically you compare your solution with a barrier. But here you cannot construct such barriers because your coefficient depends on your function itself. It's very tough. And what you do is we make a Taylor expansion, and then there is a condition saying that you have conditions from the fact that you have a maximum at the point, then look at the balance of the terms, then you get a contradiction. So it's a little bit different proof for the strong maximum principle. Okay. So now let's look at the and then we can say a stronger version of the story. Since our eigenfunction is a strongly log concave, and my second differential of the solution is converging to the second differential of the eigenfunction, which is negative, so this one will be negative in finite time. So in the other words, my parabolic flow will be strictly log concave in finite time. And then linear case. So now you have an eigenvalue problem, I want to approach the eigenvalue problem through the parabolic flow. And then if P is less than 1, then we can consider this porous medium equation. Why? So porous medium equation has a self-similar solution, which has this form. It's easy to get this one because it's a separation of variable will give you this solution. Then this f of x satisfies this equation, and if if something is wrong, f to the m is pi, right? Then you have this one. And m is greater than 1, so p is less than 1. So it is a sublinear case. Okay. So you have a similar approximation lemma. It is more sophisticated, but it's a similar story. And then we already showed if initial data is if we have a square root concavity of the initial pressure, then it will stay like that forever. So we have a square root concavity of the pressure, and then square root of concavity of pressure corresponding to the concavity of this term. And this is exactly the same result with the Cavos. And you can show the stricter root to concavity and also eventual square root to concavity of the pressure in finite time. It's the same story, but it takes a much tough computation, but basically the same story. And then what about the superlinear case? And that one is corresponding to this flow. And it's a porous medium equation, but m is less than 1 now. And this number is bigger than this critical number. And this critical number is the critical number for the nonlinear eigenvalue problem. It's corresponding to each other. And then the parabolic flow has different phenomena. And since it is a fast diffusion, the influence of zero boundary data will make a fast influence into the inside. So what happens is if you have, so the story is the following. So now m is less than 1. So if u is very small, then your diffusion is very strong. So let's say you have initially, you have this solution. Then at a certain time, all of your solution is identically zero. It is the extinction time, because the influence of zero data is so strong. So, and that makes a very tough difficulty. So we have lots of important estimate, and basically this one says at a finite time, your solution is identically zero, so that is extinction time. And we have approximation, but the approximation is a little bit different. So in the porous medium equation, you can take a different time slice and take a limit, then you end up with the elliptic problem, elliptic solution. And the elliptic solution has a uniqueness. So you can take any time. So basically you have nice convergence. But in the fast diffusion case, if you take a time slice and take a limit, then you have elliptic equation, which we don't know the uniqueness in the elliptic problem. So we just have this approximation of the time slice, and that's it. Okay, that is one difference. And the other difference is instability. So when you make an argument, so this is t is 0, then you have your initial data, and this one will be 0 at a certain time. And now you want to control your flow, so you put the sub-solution and super-solution. And sub-solution has a different extinction time, and super-solution has a different extinction time. So it's very tough to see the behavior at the extinction time through these barriers. Basically, you cannot capture it. Somehow, that's the instability, somehow. And then that is really corresponding to the difficulty in the superlinear case in the elliptic problem. So difficulty doesn't go away somehow. Okay. But our method works. So at least we can show through that method there is a solution. We don't know the uniqueness of the solution, but there is a solution which has a geometry structure. And now P is less than 1. This P is greater than 1, so you have a convexity instead of concavity. But basically method works. Now, let me talk about the Gelfand problem. So Gelfand problem is you have exponential nonlinearity here, and this problem comes from many applications. One of them is combustion theory, and I just copied it, I don't know well. But I know the combustion problem, but the other problem I don't know. But you have lots of application, and there is a very interesting research, and it says the following. So you have a very critical lambda star, and if lambda is greater than lambda star, and there is no solution, even in distribution sense, and if lambda is smaller than lambda star, then you have a solution, and also you have a minimal solution. So that is the smallest solution among the solution. And that is the solution that I'm interested in. And then if lambda is lambda star, then there is a unique solution. And then Galarias and Grossi showed such a solution will have a convex level set if lambda goes to 0. So if lambda is pretty close to 0, then you have some geometry structure.
What is the minimum solution?
Minimal solution?
The theory this one right now. This is the minimum solution.
Yeah, it's a minimal solution. Yeah. And main question. So we have now new elliptic problem. So which parabolic flow are we going to use to approximate this minimal solution? That is the most important question because we know computation. So then I tried a lot of different flows to attack it. And then the requirement is the following. The first one is a long time existence and the convergence to the elliptic solution. Well, if it doesn't have, I hope a long time existence. Well, but in the first diffusion case, we don't have a long time existence, but still it works. But I hope it has a long time existence. And the second one requirement is the conservation of the geometry structure. So then I tried a lot of flow, and I end up with this one. And maybe you can write down in terms of V, e to the u. Then you have V and the log of V and plus lambda V. But here, I prefer this equation because I know the regularity of u, right? Then if you take a log of some u, yeah, then V may have different flavors. So, and I just looked at this equation. And then my domain is a strict convex. Then if the supremum of this u is smaller than certain number, I found this number is not optimal at all, but my barrier gave me this number. I hope I want to improve it. But anyway, there is some number. And let's say supremum is smaller than this number, then you have some f, and you have this kind of concavity. And this f is pretty simple, let me tell you. So then, what can you get about this minimal solution? So let's say the supremum of this minimal solution is smaller than this number, and let's say that number is lambda star. So how can I do that? If lambda goes to 0. So let's go back to the equation. So if lambda goes to 0, then you have Laplacian, and you end up with the 0. So minimal solution will converge to 0 if lambda goes to 0. So in the other words, you can decrease the height. Okay. So then I choose the largest lambda. so that the height is smaller than log of 16. Then if lambda is smaller than this one, then we have this concavity. And this f is actually a very simple linear function. And also one of the important things is the following. So if you choose your initial data, which is smaller than this minimal solution, then this is a parabolic solution cannot cross this elliptic solution. It's a kind of upper bound. And also, at the limit, this one doesn't go to 0 because 0 is a sub-solution. So it will converge to some stationary solution. No other, it will converge to this one. It has no other choice. So then I will choose a very nice geometry, initial data which has a geometric structure. Then this is a very general computation. So let's say your W has this form, then I want to show W is concave. Then each one will have certain structure conditions. And then these two structure conditions is pretty easy because if you throw the second differentials and then you want to make it negative, that's why I make it concave. And what about this condition? This condition comes from our changing directions. So you have this term, and then you have the better term, which I mentioned to you. So I will select C alpha so that this is 0. Right? And Laplace of W is non-positive because it was complete. And then I require this term is positive. Then all of these things will be negative, so it will be a good term. So such a requirement will give me this condition. And then now I have my parabolic flow, and now I'll plug e to the u. I plug f of w in the e to the u and derive the equation, and then match the structure condition. Then I end up with a couple of conditions here. But I have another condition. So let me tell you this one, and this is the last part. So, and that condition comes from the boundary. Under the boundary, u and u sub t is 0. So, you had e to the u, right? And the e to the ut is 0. And you have e to the u, but u is 0, so you have 1. You have lambda. And then you have tangential second differentials and the normal second differentials. And then you have this balance. And then this balance gave me, okay. And what about the equation for W? So you write it down. And I expect this one is negative. Then you have some condition, you have some terms here. And I expect this is negative. From there, I have that condition. So time is almost done. So let me skip it. And then I try the many functions, and then that function works, basically. And for the nonlinear equation, there are a couple of issues, like I don't know what is the critical exponent. And also, I have some Hanok estimate to show my solution is stays positive, and that is the difficult part. And basically, I can tell the same story if f is concave. And the question is, well, is concavity of f sufficient, necessary condition to show log concavity? So in the other words, if you have solution, if f is not concave, then your solution may not log concave. So that's I feel a little bit comfortable, but we need to prove. And thank you.
So concavity for the Fourier